Hello everyone, welcome to the third week of this course on measurement and instrumentation. This is part of module 2 where we are talking about analog meters, and this is essentially the first lecture of this third week and 11th lecture of the course as well as 6th lecture of this module 2. In today's lecture we are going to discuss about operating torques in the electromechanical indicating instruments. Let us try to understand first what are the different torques which is essentially required for a analog instrument to operate or to function properly. Okay. So, three types of torques are needed for a satisfactory operation of any indicating instrument, and these torques are basically deflecting torque that we have also discussed in the previous class, TD, the controlling torque TC, and the damping torque. Okay. We will discuss about all these torques in little detail. Of course, this discussion is beyond the say particular instrument. So, we are not targeting particular instrument, but what is the goal of this lecture is to just introduce you to these torques and how they are actually essential for the satisfactory operation of any analog instrument. So, these torques are irrespective of what kind of instrument you are studying. Of course, we will discuss about all these torques for that particular instrument, which we will take one by one maybe in the later modules or in the later lectures. Okay. So, let us first try to understand the deflecting torque first. Okay. So, the deflecting torque, sometime also known as the operating torque, is required to move the pointer from its 0 position and is proportional to the measured quantity. The measured quantity can be any electrical parameter, maybe its current or voltage or say power or energy. Okay. So, essentially the pointer was at 0 position, okay, and any deflection in this pointer's position is basically a mechanical effect, and this mechanical effect is because of some electrical phenomena in the background, right. This can be, as I have mentioned, the current, voltage, power or say energy, right. And this deflecting torque is very essential for any kind of reading. So, because of this deflecting torque only you are able to see the readings on your scale. Okay. The system producing this deflecting torque is called the deflecting system, as well as it is also known as moving system, because we are also calling this torque as operating torque. Okay. The deflecting system of an instrument converts the electrical current or potential into a mechanical force, as I have just mentioned, which is basically the deflecting torque, right. So, to produce the angular deflection of the moving system, mostly the pointer, in response to the electrical quantity is what all about this deflecting torque. Okay. This quantity that I want to measure usually is proportional to the torque. Okay. However, this proportionality is not fixed to be linear, it can be a non-linear factor. Okay. So, TD is actually proportional to the quantity that we want to measure, but with a factor n. So, we cannot say that it is always linear in nature. Okay. This quantity, this Q, is mostly the current, voltage or whatever factor we are discussing. Okay. So, if you remove this proportionality constant, this torque is actually equal to some constant which is known as a deflecting constant and depends on the instrument design. Okay, and multiplied by this quantity which is being measured to the power n. Okay. So, the value of n depends on the what type of instrument you are talking about. Like for example, for PMMC instrument, this n is 1 and it changes from 1 to say 2 for another set of instrument like moving iron kind of instrument. Okay. So, there can be different ways by which this deflecting torque can be produced. Okay. It can be produced by electromagnetic effect, It can also be produced by certain electrostatic effect or by heating effect. You can also have, say, induction effect because of the AC currents, Hall effect, piezoelectric effect, etc. And this will depend on the type of instrument. We have understood all these effects and how analog instrument can utilize this effect in their operation in our previous lectures, where we discussed about the classification of analog instrument in detail. Okay. In a moving coil kind of instrument, the deflecting torque is basically, say, for example, produced by the interaction between the magnetic field and, say, the current carrying coil. Okay. Similarly, in the electrodynamometer kind of instrument, you have already seen that two magnetic fluxes interact with each other and it produces deflecting torque. Okay. So, as I have mentioned, there can be various ways by which this deflection can be produced, like as I am mentioning about the electromagnetic effect. So, mostly this electromagnetic effect are used in, say, PMMC or moving iron kind of instrument, and based on the interaction between a magnetic field and current carrying conductor, you have a torque developed, which is the deflecting torque. Okay. So, the deflecting torque which is produced in this case is mostly proportional to this TD is mostly proportional to the current I. It is also proportional to the flux value, right. So, we have seen this, the basic torque equation for PMMC instrument, for example. Okay. So, when you have this torque proportional to the current proportional to the flux, okay, the equation of the torque looks something like this. Torque is proportional to or is equal to certain value K multiplied by this B and I. Okay. We will take this, we will try to understand this K when we will talk about PMMC instrument in more detail. Okay. So, this way of producing deflecting torque, which is of course based on the electromagnetic effect, are mostly found in PMMC tools as well as the moving iron kind of instruments. Okay. There are other ways of producing a torque, like deflecting torque, like the electrostatic effect. Okay. Mostly this electrostatic effects are localized in the electrostatic tools like electrostatic voltmeters. Okay, and they work on the attraction on repulsion between the charge plates. So, deflecting torque is proportional to the square of the applied voltage. Okay. So, mostly this TD is is directly proportional to V square, and if you have this TD is equal to, say, some constant, okay, into V square. Okay. We will see this value of K in more detail when we will discuss about the electrostatic voltmeters. Okay. These instruments, as I have mentioned, are particularly helpful in the deflection of electrostatic voltmeters. So, they are suitable for high voltage measurements. This high voltage can be any type of signal, like it can be AC signal or it can be based on DC. Okay. Similarly, capacitance type of voltage devices or voltage instruments are also based on this. Okay. Then for the induction effect, these are mostly localized into the induction kind of instrument. We have discussed the induction type of instrument when we talked about the classification of the analog meters. Okay. They work on the interaction between the alternating magnetic fluxes with the induced currents. Okay. And please note that these only work with AC quantities and not with the DC one. Okay, because you have to generate a flux. So, deflecting torque here is proportional to power or energy, or TD we have earlier also we have seen that is proportional to phi 1 into phi 2, which are the fluxes into two coils, and alpha was the angle between them. Okay. So, TD is basically directly proportional to phi 1 into phi 2 and sine of angle between them. Okay. The example can be again AC energy meters or induction type voltmeters or induction type ammeters. Okay. Now, there are other ways also of producing this effect, like piezoelectric effect or by thermal effect, and these are again thermal effects are localized into the hot wire kind of instrument because they are based on the heating effects of the current or by Joule's law. Okay. So current basically causes expansion of the wire. This was one of the technique that we have seen in the thermal effect. There were other methodologies also for measuring, for developing instruments based on thermal effects. Okay. So the current causing expansion of wire actually moves the pointer. Okay. That's how we have described hot wire instruments in our previous classes. All right. So this is basically nothing but a thermal effect. Okay. So the deflecting torque in this case also is proportional to the square value of the current flowing through the wire. Okay. And they are again suitable for both kind of signals like AC as well as for DC, and again for high frequency measurements also they are suitable. Okay. So they are applicable in hot wire voltmeters or hot wire ammeters, etc. All right. So this is in nutshell what is deflection torque and how they are produced. We will of course take them in more detail and we will write their equations, okay, when we will talk about all these instruments. Maybe it's PMMC or maybe it's moving coil or other kind of instruments. Okay. So deflecting torque, I hope that is clear to you. Now let us see another torque which is also very important in the functionality of analog instrument, which is the controlling torque. Okay. So the controlling torque, which is also known as restoring torque, is the opposing torque or force developed in a electromechanical measuring instrument to balance the deflecting torque. Okay. Otherwise, if you do not balance it, the pointer will have continuous movement and you never know that what quantity it is measuring. So if you keep on increasing current, it will keep on moving. Okay. And because even if you stop this current flowing, because of its inertia, it will try to move beyond that point. Okay. So there is basically no final point which is linked to the measured electrical quantity. All right. So therefore, this kind of controlling or restoring torque is very much required in the operation of this kind of instrument. Okay. So this controlling torque basically ensures that the pointer comes to rest at a steady position corresponding to the measured value and again returns to zero when the current or voltage or any other say power or energy is removed. All right. So the idea is to bring it to its original position and make the instrument ready for the next reading. All right. So if I summarize, the function of the controlling system which is producing this controlling torque is to produce a torque equal and opposite to the deflecting torque at the final steady state position of the pointer by again ensuring a definite deflection for a given magnitude of a current and voltage. So you are removing any uncertainty or any indefinite deflection in the pointer by utilizing this controlling system. Okay. The another function of this controlling system is to bring the moving system back to the zero position when the deflecting force which is causing the deflection or which is the reason behind the deflecting torque say be its current or voltage is removed. Okay. So once these factors are removed, the pointer should be brought back to its original position. If there is no such mechanism, even because of say retardation, if it stops say at this point, there is no way that this will return back to its original position. All right. So for the movement of this pointer, deflecting torque is very much essential. However, to bring it back to its original position, a controlling torque is very much essential. Fine. So basically this is mostly produced by a spring. Okay. Say I have, forget about this control weight for the time being. Okay. And I am connecting this with a spring. Okay. This spring has certain spring constant, for example, say Kc. Okay, and the deflection is, for example, is theta. So the controlling torque is mostly proportional to this theta value. Okay, and if I remove this proportionality, I have say Tc is equal to certain Kc value, which is a control constant into the deflection or angular deflection. Okay, and to ensure a steady equilibrium position when this pointer stops at certain position. Okay. This Tc value is equated with the TD value, which is the deflecting torque, right. So at this position, this TC is equal to TD, all right, and this pointer will come back to its original position. So this equation will ensure that, okay. So TC is equal to TD at the steady equilibrium position, all right. So we will be using this equation regularly when we will talk about the different analog instrument, okay. So if you remember, we have already seen one equation for deflecting torque, which was nothing but K into whatever quantity we are measuring to the power n, okay. So if I equate this to TD and TC, I have this KD into Q power n equal to KC into theta, all right, or theta can be written as KD by KC into Q power n, okay. So for PMMC, we have already seen that n is equal to 1, means that theta is directly proportional to the what quantity we are measuring. So say for ammeter, we are measuring say current, so theta is directly proportional to current, and then you have a uniform scale, okay. So this controlling torque is basically defining the type of scale you are using for the measurement, okay. So for PMMC tool, you have theta directly proportional to I, for example, okay, because Q I have already, this n factor I have already taken as 1, okay. So theta is directly proportional to I, means that this scale is uniform. So this value say is 0, this is 1, 2, 3, 4 and so on. Fine. For moving iron, as I have mentioned, this n value is 2, okay. Now theta is directly proportional to I square, okay. So now this scale is non-uniform and the distance between them is also of course non-uniform, okay. Say this is 0, maybe this may be 2, this may be say 4 and so on, all right. So we will take this scale in more detail when we will talk about these analog instrument one by one, okay. So I hope that this concept is getting clear for you, the controlling torque concept, okay. So one idea that you must have got till now, that basically you can use a spring to provide the controlling torque, but spring is one of the way for providing the controlling torque. The second one is the gravity control, okay. So two type of controlling mechanism is possible for the controlling torques. One is the spring control and another is the gravity control, as you can see from the figure also, okay. In this, if you can see, a certain weight is loaded to the pointer, and this was exactly what was showing over here, that I told that we will take it later on, right. So spring control and gravity control, there are two ways of managing this control mechanism, all right. So spring control is the most commonly used methodology in the current scenario, okay, and this uses two basically phosphor bronze spiral springs, okay. One spring provides the restoring torque and the other carries the current to the moving coil, okay. We will take this flow of current and other things in detail when we will talk about these instruments, okay. However, the torque developed is again proportional to the deflection value, or TC is directly proportional to the angle of deflection, fine. The advantage of using this spring methodology or spring control is that they are suitable for all the portable instruments, because you do not have that extra weight added, okay, and they provide a linear restoring torque, okay. That's why I mentioned that in the most of the case, the restoration is linear in nature, okay. However, they are affected by temperature a lot, and if your pointer is going in the plasticity zone, for example, regularly, okay, the spring will of course bring certain level of fatigue, okay. So the temperature and fatigue is two of the important parameters which actually govern the behavior of the spring in long term, okay, and that's why they are classified under disadvantages of this this spring. Okay, you have seen that a phosphor bronze, a special kind of alloy is used for making these springs. So basically you are fixing certain kind of material which can be used for fabrication of this spring, for making of this this spring. So basically you cannot use any spring that is available in the market. Okay, so there are certain characteristics which is required for this spring material. Okay, some of them are like the spring material should be electrically conductive. Okay, as in PMMC instruments which also carries the measuring current that we have just seen some time back. Okay, the material of this the spring should be non-magnetic in nature to avoid affecting the magnetic field of the instrument. Otherwise you may have localized eddy currents which will again oppose the magnetic field already produced. Okay, so the two criteria that we have just seen, one is the spring material should be electrically conductive and the material should be non-magnetic in nature to avoid affecting the magnetic field of the instrument itself. Okay, the material of the spring should have a nearly constant spring constant, which is of course a very ideal case, but then deviation should not be very high. Okay, meaning it must show very little variation with the temperature. Otherwise you may not be able to figure out that the value of Tc is changing because of the deflection for the countering Td, or it is because of the temperature. Okay, it should possess a high mechanical strength and elasticity to maintain stability during operation, basically to avoid any kind of fatigue. Okay, and that is why phosphor bronze has been chosen, because its suitability in terms of electrical conductivity, its magnetic behavior and its mechanical properties. All right. Then second kind of controlling torque or controlling mechanism can also be provided by gravitational control. Okay, so a small adjustable weight is basically attached to the spindle. Okay, so the gravity produces a restoring torque due to the displacement of weight, because with the pointer's movement this weight is also moving. Okay, and the torque is proportional to the sine of the deflecting angle. Okay, if you see this controlling torque equation, it is in this equation this W is the weight and L is the distance from the spindle. Okay, the advantage of this gravity control is it's very simple and basically a temperature independent thing. Okay, because you are not using any spring in this case. However, in this case always the scale is non-linear. Okay, and instruments must be kept vertically upright, otherwise in horizontally you will not have that effect of gravitation. Then they are unsuitable for portable instrument because of the extra weight which it carries. Okay, then third type of torque that is required for the functionality of the analog instrument is the damping torque. Okay, so these two torque, the deflecting torque and controlling torque, I think should be clear to you. Okay, and third kind of torque is the damping torque, and let's discuss that in detail. We have also covered this damping in our previous class, where we discussed about a different class of analog meters based on the damping mechanism it uses. Okay, so damping should be clear to you till now, but then also if you have doubt, let's discuss that in a brief. Okay, so in any electromechanical indicating instrument, for example in PMMC or say in moving coil, okay, the pointer moves due to a deflecting torque and stops at certain angle, say theta, when controlling torque balances it. This we have already seen. So Td is equal to Tc is the condition when basically this pointer will stop. All right. However, before reaching this steady position, the pointer tends to oscillate around its final value. Say if this is a pointer, say this is the final position, say initially it was here, okay, and it reaches this O position. Now at this position O it should stop, but usually it will oscillate between this point A and B. All right. So to prevent these oscillations and ensure the pointer reaches the final reading quickly and smoothly, a damping torque is introduced. Okay, so to avoid this over damping or under damping or overshoot or undershoot, okay, you utilize extra damping torque, okay, to avoid any kind of oscillation. Okay, so the damping torque is a resisting torque that acts only when the moving system is in the motion. Okay, so it always acts in a direction opposite to the motion of the moving system, thereby reducing oscillation and enabling the pointer to reach a steady position promptly. Okay. So, there are certain this torque, damping torque, is produced by, as the name suggests, by the damping system, and there are certain requirements of the damping system. Okay. So, for example, damping torque must act only during motion. Okay. So, damping, as I have already mentioned, will not be applicable when the system is at the rest position. Okay. So, damping torque will only act when this pointer is in motion and is about to say reach its steady state or its final position. Okay. And this damping must oppose the motion of the moving system. Okay. And it must not affect the final deflection or the steady position which this pointer is going to achieve. Okay. So, I think the purpose of the damping torque should be clear to you, that it is to ensure the pointer reaches the steady position quickly without any oscillation, and without damping pointer will definitely oscillate for longer time before settling it up. Okay. And it will make this system unstable for good amount of time. Okay. And you may not be able to find the correct value in the stipulated time. Okay. So, therefore, the damping forces are necessary so that the moving system comes to its equilibrium position rapidly and smoothly without any kind of oscillation. Okay. So, with this, I think the requirement of the three torques are very much clear to you. We have discussed about the deflecting torque, which is essential for pointer's movement. We have also seen a controlling torque, which is required to stop the pointer at the steady state position. However, the controlling torque is not sufficient enough to avoid the oscillations at the edges where it is going to achieve the steady state value, and that is why we take support of another system, which is damping system, to provide the damping torque. Okay. So, with these three torques applicable, say deflecting torque, the controlling torque and the damping torque, the analog instrument will function properly. Okay. So, we will meet in our second lecture of this third week with another topic. Thank you.